Hello, welcome to Magnetic Levitation System Modeling with Aiden Durr and Cowan.
Problem statement. One of the problems the United States faces in today's society is the lack of infrastructure, more specifically in the travel sector. This is crucial in order to have a functioning economy and a prosperous country. If a person is unable to go from point A to point B in a fast and reliable manner, then time and efficiency is lost. As a possible remedy to this issue, the United States should start implementing mass transit in the form of magnetic levitation trains to make up for lost time.
The first maglev concept was patented in 1934 by Hermann Kemper of Germany. Over the next few decades, these maglev systems would go through countless hours of development before being able to be used by the public sector. China was the first to complete this goal in 2003. They created an electromagnetic suspension system, or EMS, for public use. China was then followed by Germany's EMS system and Japan's electrodynamic suspension system, or EDS. The United States, however, has still not made a mass transit maglev system open to the public use.
A maglev system uses electromagnetic forces to suspend an object in space. The two types of forces consist of a repelling force, which suspends the train off the track. The other force is used to propel the train along the track using alternating poles. The benefits of this application is that the object will be moving along a frictionless track. It will also not consist of movable parts. These maglev trains can reach a top speed of 375 miles per hour, but only go up to 270 miles per hour for public use. There are two types of systems. There's the electromagnetic system and the electrodynamic suspension system. In this presentation, it will be based upon the electromagnetic suspension. Coils only conduct electricity when power supply is present. An electrodynamic suspension system, it uses supercooled, superconducting electromagnets. The conductors are exposed to time-varying magnetic fields. This induces eddy currents in the conductors. The eddy currents create a repulsive magnetic field which holds the two objects apart. The coils can still conduct electricity after the power supply is cut off. The magnets on the side of the track are put in a figure-8 configuration so that the train hovers in between the two forces.
Model of levitating object. Here we have a simple free body diagram of an EMS system. The goal of the model is to find the transfer function y of s divided by v of s. This will allow us to see a relationship between the voltage and the distance. The forces acting on the car body include a primary suspension force, F mag, which is in the form of electromagnetic forces. There is also a secondary suspension force, P, and a mass of the train, m. On the kinematic side of things, there is a downwards acceleration, my double dot. In equation 1, it includes the variables F mag, which is a primary suspension force, C, which is a constant related to the turn ratio and cross-sectional area of the electromagnet. L is the length of the solenoid in meters, and I, which is the current through the solenoid wire in amps. In equation 2, P is the secondary suspension and is equal to a spring damper system. In equation 3, we equate the equations of motion. In equation 4, we substitute the equations 1 and 2 into equation 3. In equation 5, we take the Laplace of equation 4. And finally, in equation 6, we solve for the transfer function y of s divided by I of s. Transfer function of the track and object. For this system, we are solving the transfer function y of s divided by v of s, which we will give the distance between the car body and the track at a specific input voltage. In equation 7, KVL is used to find the equation for the system, where V of t is the voltage input into the circuit, R is the resistance measured in ohms, and L is the inductance measured in henries. In equation 8, we take the Laplace of equation 7. And in equation 9, we are solving equations 8 for I of s. In equation 10, we are substituting equation 9 into equation 5, and in equation 11, we are solving for the transfer function y of s divided by v of s. Finally, the transfer function y of s divided by v of s can now be plotted using MATLAB.
In MATLAB, we substitute arbitrary parameters into the transfer function to determine the plot of the displacement between the car body and the track over time. On the plot of the transfer function, the distance y oscillates between 0 and 9 millimeters. From the transfer function, we can obtain the natural frequency, which is 1.15 radians per second. On the Bode plot, the magnitude is negative 78.2 decibels, and the phase shift is negative pi. Increasing the length of the solenoid, resistance, inductance, spring, or damping coefficients in the transfer function would make the oscillation displacement smaller. The length of the solenoid would make more of an impact on the transfer function plot than the other parameters. Increasing the size of the electromagnet would increase the displacement between the car body and the track. A typical EDS system will levitate anywhere between 2 millimeters to 15 millimeters off the track. This depends on the mass loaded on the train body. Our model's levitating displacement falls within the range of the actual systems used in the real world. However, the model of the system can still be improved. For example, eddy currents were not considered in the model, which could be used as a magnetic friction force. There is also the possibility of disturbances from the surroundings, such as air or vibrations from the ground. The material of the magnet could also affect the magnetic force. Also, the secondary force was simplified to be a spring damper system when it really includes the lateral guidances within the electromagnets. For more information on electromagnetic systems and electrodynamic systems, please visit the links on the references page.